So we are now going to be doing box and whisker plots, box plots, and we're also going to discuss outliers today. So be really careful if you're going to use things like this in your IA. Be really careful with use of the term outlier, because something is only an outlier if the math says it is. It's not an outlier simply because it's outside of the normal set of data. That's not what an outlier is. Okay. So a box plot, or box and whisker plot, is a visual display of some of the descriptive statistics of a data set. It shows 5 very important numbers. Those 5 numbers are minimum, maximum, Q1, Q2, Q3. So let's put the minimum value, the lower quartile, which is Q1, the median, which is Q2, the upper quartile, Q3, and the maximum value. Those 5 numbers form what, I don't know if it's just our textbook authors or if it's IB in general, they call the 5-number summary of the data set. There, the 5-number summary of the data set. So I've put a box and whisker plot up there for you. And the box, the edges of the box are Q1 and Q3. The median will just be a vertical line that's inside the box somewhere. Now the minimum value and the maximum value will just be dots, end points, basically. And the whisker is a straight line that goes from Q1 to the lowest value and from Q3 to the maximum value. And if you need to know the IQR, the interquartile range, again, you would just do Q3 minus Q1. And that's how wide the box is. The rectangle of the box represents the middle 50% of the data, middle 50% of the data. The whisker, the lower whisker from edge of box to minimum value is the lowest 25%. So 25% of the data with the smallest value. 25% of data with smallest value. Sorry about the handwriting being especially bad today. For some reason, even though it's a brand new pen tip, it's already squeaking and it's driving me nuts. So I'm trying to write in a way that makes it not squeaky. And the upper whisker represents the 25% of the data with the largest values. So it's great if you can make a box and whisker plot, but it would also be nice to be able to interpret a box plot, right? Because the shape of the box plot tells you something about the distribution's shape as well. So this first one is a set of data with roughly symmetric distribution. So if you look at this box plot, you can see that it's roughly symmetric as well. This one, the next one, it peaks to the left, so this would be positively skewed. And look at this box plot. Now, I like this box plot idea here because I think it really, really shows you why we call this thing positively skewed. Look at how much stuff there is to the right of that blue line. There's so much more stuff on the right of it than there is on the left. And that's why we say it's positively skewed, because it's letting you know where the majority of the data lies. Not where the mode is. Obviously, the mode is the tallest graph, the tallest box. But you could see that there is a lot of information to the right of that median. And this last one, they just did that with a dot plot, which is interesting, but you can see that it spikes to the right, so it would be negatively skewed, and the box and whisker plot shows you that. I mean, there's a lot of stuff to the left of that Q2, a lot. So something that people talk about wrong a lot, outliers. Again, an outlier does not mean that it is outside of the normal data. Don't use that term that way. Now, outliers are either much larger or much smaller than most of the data, and you use an equation to decide if whether or not something is an outlier. You can't just be like, well, that one's really outside the data, so that's an outlier. No, technically, you need an equation. Now, I don't know why this equation is used. I'll just be honest. I don't know enough about statistics to know why the equation is what it is. Okay? And to be honest with you, I don't like statistics enough to care to go look it up. I mean, it is what it is, okay? But it be what it be. A test is used to identify outliers, and that involves the upper and lower boundaries. So it involves finding the upper and lower boundaries. I don't know why the boundaries are found this way, but they are. Okay. What you do is you take your interquartile range, you multiply by 1.5, and then you either add it to Q3 or you subtract it from Q1. So the upper boundary is Q3 plus 1.5 times the IQR. And the lower quartile is 1.5 times IQR less than Q1. So Q1 minus 1.5 IQR. Everything outside of that would be an outlier. So on the box and whisker plots that we just did, I specifically said that the dots are the minimum and maximum value. Technically, that's not true. Technically, the two dots, the endpoints, quote unquote, are the upper and lower boundaries. Because outliers will be marked with an asterisk on the box plot. So the two dots will not always be the minimum and maximum. The two dots will always be the upper lower boundary. But you will always be able to see the minimum and maximum values on the box and whisker plot, always. Just sometimes one of them or both of them could be an outlier, or neither of them. It doesn't matter, but it happens. There may be more than one outlier at either end. That happens. The whiskers do not go to the outliers. The whiskers go to the upper and lower bound. There we go. Is this ordered? Oh, crud. It's close, though, isn't it? All right. It's okay. I have it ordered. I have it ordered. Yes, I know. That's Katie's favorite thing, but I have it ordered. There it is. So part A says to construct the 5-digit summary. The 5-digit summary. That means we need to know our median, and then after our median, we'll work on Q1 and Q3. So let's see. How many digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 digits. That means, since there's an even number, that our median would be 20 plus 1 divided by 2, or the 10.5th term. So that's going to be the average of the 10th and 11th term. The average of these two terms is our Q2, which is obviously 8. Now remember, those two 8s, they are still part of the left half and the right half. So when you go to find your Q1 and your Q3, you have to include that 8 as part of that set. There are 10 terms to the left of Q2. So 10 plus 1 divided by 2, the 5.5 term, you're looking for the average of the 5th and the 6th term. 2, 3, 4, 5, 6. So your Q1 is 6.5. Same thing's going to happen for Q3. The average of 10 and 12, so Q3 is 11. Did I count wrong? I counted wrong. How about that? 1, 2, 3, 4, 5, 6. Yep.
Oh my gosh.
Mistake, not me. Okay. There it is. Squeaky pens throw me off my game. There we go. Q1, Q2, Q3, and minimum and maximum. Well, we know the minimum is 1 and the maximum is 16 because, well, there they are, right? Find the range and the IQR. So range, that's B. The range is just going to be the maximum minus the minimum. The IQR is going to be Q3 minus Q1. Or 3.5. So it says test the data for outliers. So what we need to do is we need to figure out our upper bound and our lower bound. Okay, so we have to do RQR times 1.5. And let's just scroll down a little bit. I'll scroll up and down. I'll squeeze the box plot over there. C, all right. So our lower bound, how about we use LB, elbow, lower bound, is going to be Q1 minus 3.5 times 1.5. Our lower bound is a decimal, I don't know, 1.25. I didn't know the answer. Our upper bound is going to be 10 plus 3.5 times 1.5. 15.25. So any number smaller than 1.25 would be an outlier. Any number larger than 15.25 would be an outlier. So that means that we have 2 outliers. We have an outlier at 1, and we have an outlier at 16. Wait, what? 3.5 is the IQR. I switched the 2 numbers, I know, but multiplication doesn't really care. So construct a box plot. I'll do it over there. I have space over there. Part C, part D, box plot time. And my numbers go from 1 to 16. I'm going to do my best to get them all on there, and I will do my best to get image drawn to scale. Nope, that's not good. So if that's 16, here's 8, here's 1. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's pretty good. Close enough. I'll put a 5. There's a 10 right there. You can see where 16 is. I'm just trying to get a couple digits on there that matter to us. All right, let's make a rectangle. What color do I want my rectangle to be? Just to see the scale. I was just getting more numbers on there for scale. I could put 15 up there too just to see. I just did it for fun. I'm going to do orange. Okay, my Q1 is at 6.5. That's here. My Q2 is at 8. That's here. And my Q3 is at 10. Yeah, it's a little box. My whiskers are going to go out to 1.25 and 15.25. Hey, Gavin's back there swearing. And our asterisks would be at 1 and 16. There. But they are, mathematically. What does that mean? I'm not really sure. I'm sorry. But if it's interesting to you, you could always make that an IA concept. I'm just saying. And I would enjoy reading that because then I would learn something. Because I don't care what the correlation between pitcher height and number of strikes is. Sports IAs are boring. Boring. E says find the percentage of data values that are less than 8. Well, okay, so you literally just count how many data values there are. There's 20 of them. And how many are less than 8? 8. Agreed. So that is 0. Was it 4? Yep. Or 40%. Because it says find a percent. There you go. It's supposed to be a percent. I'm sorry? Oh, she's upset that the next one is arranged. Okay. Shucks, I hate it when my life is easy. Alrighty, let's see. What we got going on here? A hospital is trialing a new anesthetic. They've collected data on how long the new and old drugs take to work. They want to know which drug acts faster, but which one is more predictable, because these are both things that matter. So what we're going to do here is we're going to draw a parallel box plot. Because they're representing the same kind of information, we could put two different boxes on a single, for example, x-axis. A single horizontal axis can have two different plots. So we have old drug times, we have new drug times, and we're going to need some information, right? Let's see. How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 digits again. 20 digits again. So for old, let's do all our old information here. Our Q2 would be halfway between the 10th and 11th one. Well, that makes life easy. It's 10. Our Q1 is halfway between the 5th and 6th term. So it's 8. That makes life easy. And our Q3, halfway between the 5th and 6th term here, is 12 and a half. 5th and 6th term is 12 and a half. We are not going to look for outliers here. Not really important because the question wants to know which one acts faster and which one acts more predictably. You see, what we have here is information on how long it takes to act. I mean, just looking at it, it looks like the old drug time has a wider, I mean, you could see its range is much wider. It could take anywhere from 5 minutes to 21 minutes. The new one could take anywhere from 7 to 12. So much smaller range. But which one is more reliable? Let's see. Color we want to do the new one in. I got a little colorful. I'll do the new one in orange. Q2 for the new one. Same setup. Halfway between these two 9s. Luckily, they stacked the data for us, so I can already see where the boxes are. Q3 is halfway between these two 8s. Excuse me, Q1. My apologies. Q3 is halfway between these two 10s. Box plot. Parallel box plot. Let me give myself some space. Oh boy, this thing's got to go from 5 to 21. That's a lot of numbers. That's a lot. 16 things, isn't it? So let's say we started at 5. There's 10. There's 15. There's 20. There's 21. Picture art drawn to scale. I did my best. Forgive me. So I'm going to draw the old box plot in red, the whole thing in red. Q1 was at 8. Q2 is at 10. Q3 is at 12 and a half. Minimum of 5. Maximum of 21. Good gravy. And I did the new one in orange. Q1 also at 8. Median at 9. Upper quartile at 10. Minimum of 7. Maximum of 12. Wow. So this is new. And this one's old. So, looking at these two box plots, we're supposed to compare the two drugs. Well, which one is faster generally? And how would you know? Okay, so which one has the chance of acting the fastest? Old one, clearly. It has a chance of acting the fastest, right? But look at its median. Its median is at 10. 50% of its data, 50% of the data goes between 10 and 21. That means this thing is very positively skewed. So majority of its times are going to land, not a majority, at least, I don't even say it like that, half of its times will take longer than 10 minutes. But if you look at the new one, its median is at 9. Its maximum is at 12. So 50% of its data is between 9 and 12. So I would say that even though the old one has the chance of acting faster, the new one is generally the faster acting drug. I would argue that. So which one's more predictable? I would say the new one because, 1, its range is smaller, and 2, its upper bound and lower bound are relatively close to the median. That means this data is not spread out very far, so that's pretty predictable. That's what I would say there. Now, I want to know exactly what the book has to say about that, because the whole which one acts faster thing, I'm curious to know what their exact explanation was. This is chapter 4, correct? No, it can't be. Chapter 20. No, we're in unit 20. I mean in this book. It's in chapter 12. I really want to know what they say. Okay, here's what they said. They said the new drug is generally a little bit quicker. And the reason why it says the median 50% of the time, the new drug takes 9 seconds or less. So they actually went with its lower amount of information. And they're like, look, 50% of the data falls between 7 and 9. And if you look at the other one, 50% of the data falls between 5 and 10. So they're saying compared with 10 seconds for the old drug, the new drug is generally a little quicker, is what they're saying. The new drug is generally a little bit quicker. And the new drug times are less spread out, which is exactly what we said. So they said the new drug is more predictable because there's less, to use a term that we're going to be more specific about soon, less variance. It doesn't vary too far from the median. And that's all there is to box and whiskers and parallel box plots.